Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work. For this particular problem, we want to determine the equilibrium position as well as to find the stability for the position. Right, we have this. Okay, and we have a spring force here. Let's call it F sub S, with a S, the displacement, right? And the spring force, the spring has a constant. The spring stiffness is given in the question. Okay, this is A and this is point C. Let's call here point C, and here's point B. Okay, we have the mass, the weight of this member downward. Let's call it W. Right. Of course, there's an angle theta here. To solve the problem, what we will do is to uh, determine the potential function considering the spring as well as the weight of this member AB. Okay, so the spring force of S and the weight of this member, and from potential function that is gotten, we will differentiate it to get set it to zero to get our potential our a position, as well as determine the stability from taking a second derivative. All right, okay, solving, right, to get find stability. So for this one, we have this. Okay, then we can just determine for the spring. We take this one down like this. We can get this vertical height. Sorry, for the member AB, you can get this vertical height to know the potential, determine the potential energy. And you can see that it is below uh, the datum. You can see that the center of gravity here for this member is below datum AC. All right. So we are going to have this place to be L, sorry, half L sine theta. Okay. Therefore, for AB, for link AB, that member, we are going to have the potential, gravitational potential energy there is going to be negative. It's going to actually give us negative half uh, mg sine theta. Okay, half L, that is the length of AB, half the length of AB, that's sine theta. So we have that there. So we can proceed to the for the spring. If we look at that, we can apply the cosine rule to solve to get our S. Remember that this place is given as 0.4 meters, and this other side, which is AB is given as also 0.4 meters. Okay, so if we do that, we can just have our uh, S squared, okay, along this side. Okay, if we do that, it's going to give us S squared is going to give us equal to 0.4 using the cosine rule, 0.4, okay, plus 0.4, 0.4 squared plus 0.4 squared minus 2 into 0.4, okay, times 0.4 cos theta. So we're going to have that. So we can just make S the sum of the form. Find S rather. I'm going to have it to be equal to 0.4 in this root. 1, sorry, 2 into 1 minus 2 into 1 minus cos theta. So we have that for S. Now for the spring, we have the elastic potential energy to be equal to half, sorry, which is K S displacement squared over 2, which is still the same thing as saying, okay, where F, sorry, F is, let's put it down here, where F, we know that F is equals to K, KS. Is that okay? F is equal to KS. All right. So we can just plug in values into, we'll get a potential function V is equals to V G plus V E, that is a gravitational potential energy as well as the elastic potential energy. So we have that. So plugging in our values for the gravitational potential energy is going to be 3. Okay, so let's just go. It's going to be give us minus. Said earlier on that this one will give us negative, and I'll explain why. Half. Okay, 0. Times 0.4. Okay, which is the length of AB times minus 3. So we have already indicated the negative sign already. Times 3. Okay, times 3 times 9.813 is the mass of length AB sine theta. Okay, plus the spring stiffness there for the, which is 100 Newton per meter given, over 2 times the S squared, the displacement there. So of course, looking for S, squaring it, we are going to have it to be 0.4. So let's just do it this way. It's going to give us times 0.4, okay, squared into 2 minus 1 cos theta. So we're going to have that. Okay, on squared, that's what we're going to have, right? So we can just bring in everything will not turn out to be, when we multiply this out, it will give us minus 5.89 sine theta. Okay, plus 16 into 1 minus cos theta. So we have that. So we can now take for the equilibrium position. For equilibrium position, as I said earlier on, we're going to take the derivative of the function with respect to theta, which will now give us with respect to theta, which will now give us minus 5.89 cos theta, okay, plus 16 sine theta. So equate it to 0. So if we solve this out, we are going to have theta. So just solve it. You have theta to be equal to, in fact, we come to the area you actually have to take the arctan. But when you divide cos to divide sine, you're going to have a tan. So you're going to have theta to be 21.31 degrees. Okay. All right. So that's the equilibrium position. So for the stability, we will, for the stability, we'll take the second derivative, the squared v, the theta squared. So if we do that, it's going to give us 5.89 sine theta, 5.89 sine theta. Okay, so we have this plus 16 cos theta. Now we plug in our position of 21.31 to this, we will arrive at this to be equal to 17.05. Just plug in our position into what we have there for the second derivative. We have this, and you can see that this is clearly less greater than 0. So we have a stable. So for that position, the equilibrium is stable. Okay.